Hello statistics students, my name is Jami Emigh, and this video is our discussion on section 7.1. Let's get our titles written down. Chapter 7 is on confidence intervals. You'll sometimes see that as capital C, capital I, confidence intervals. And section 7.1 title, estimating a population proportion. All right, p hat, or what we know as the sample proportion, can be used to construct a confidence interval for a population proportion p. What is a confidence interval? I saw one in the media the other day. It was about temperatures. It said that the temperature in this particular location at this particular time was going to be 55 degrees plus or minus 2 degrees. So that is one example of a confidence interval. Let's look at the notation for a confidence interval. There are 3 different ways to write it. We can go with whatever we calculated as our sample proportion, plus or minus capital E, which is some margin of error. So using that temperature example, the p hat would be the 55 degrees, and then we said plus or minus, and our margin of error was 2 degrees. We could also write it in interval notation, where we open parentheses, and we put our lower limit. Okay, this right here is the lower limit. Using the temperature example, this would be 55 degrees minus 2 degrees. That would give us 53 degrees as what we call our lower limit. Then you do a comma, and then this is how we calculate our upper limit. Using the temperature example, that would be 55 degrees plus 2 degrees. So that would be 57 degrees. And that right there is called our upper limit. So instead of just saying, we believe it's going to be 55 degrees at this location at this time, what we've done now is given ourselves a range. We can say we are with some level of confidence that the temperature will be between 53 and 57 degrees. Third way to write that same interval is using inequalities. This is the same lower limit. And then we say that that will be less than what we think the actual population proportion will be, which is less than what we think or have calculated for the upper limit. P hat is what's called the best point estimate. I like to think of it as the best guess. If we go gather some data and then we calculate p hat, our best guess is that p hat is equivalent to p. Another way to say that is, if we go gather some data and we calculate p hat, our best guess for the population proportion is whatever we calculated from the sample proportion. P hat can be calculated the way we're used to, which is x over n. We've seen that in previous chapters. X is the number of successes over lowercase n is the sample size. An additional way to calculate p hat is if you already have the confidence interval, then you can take the upper limit, add the lower limit to it, and divide it by 2. Another way to say that is it's the average of the upper and the lower limits. It's right in the middle. The capital E represents the margin of error, and that'll sometimes be given to us, and sometimes we'll have to calculate it. If we have the confidence interval, we can work backwards to figure out which margin of error they used by taking the upper limit less the lower limit and divide that result by 2. Common confidence levels. Okay, please note that this is confidence levels, contrary to confidence intervals. Confidence intervals, or CI, is what we've been talking about so far. But confidence levels, CL, is the level at which we are confident in our confidence interval. The common confidence levels are 90%, 95%, and 99%. Please note that 95% confidence is the default, and any study using a different confidence level should state that. So that confidence interval that I saw in the media about temperature the other day, which I'll just restate it, it said that the temperature in this particular location at this particular time was going to be 55 degrees plus or minus 2 degrees. Then I looked a little further to see if that study stated their confidence level. It did not state it. So I am to assume that the default confidence level of 95% was used. Any study using anything else needs to make sure they clearly state that, because the confidence level is going to determine how large the confidence interval is. Let's look at an example. 250 randomly selected people were asked if they rented or owned their own home. 99 of those people said they owned, 135 said that they rented. Find the best point estimate of the proportion of homeowners. Okay, so for this one, we will use our formula from previous chapters. We can find the best point estimate. Notation-wise, that's p hat, which is equivalent to x over n. X is the number of successes, and we were asked about homeowners. So it's 99 out of our sample size, which was 250. And that is approximately 0.396. If you want to think about it as a percentage, just to wrap your mind around it, I would say approximately 40% of the people surveyed said that they owned their home. All right, so now that we have our best point estimate, we're going to add and subtract some margin of error to it to construct a 95% confidence interval for what we believe the true population proportion of homeowners is. In this question, we are given the margin of error. It's right here. This is our capital E. So they want us to be within, I'm going to think of it as a percentage for a second. They want us to be within 6%. Okay, so what we do is take our p hat, we subtract out the margin of error. That's going to give us our lower limit. We take that same p hat and we add the same margin of error to get our upper limit. So this right here is the interval in which we are 95% confident contains the true population proportion of homeowners. If you want to think about it percentage-wise, we would be saying about or somewhere between 34% and 46% of people own their home. All right, part C says find the best point estimate, which we already did, but they want us to use a different method. They want us to use the confidence interval limits. Okay, so if for some reason, you guys, if we didn't know the 99 and the 250, so we weren't able to use this for whatever reason, but we did know this, we did have the confidence interval here, and we want to work backwards. Okay, well, what was the best point estimate used? We'll take the upper limit, add to it the lower limit. After the addition takes place, we'll divide by 2, and that is a different way of finding what the best point estimate was using the confidence interval limits. Similarly, if we're asked to find the margin of error, so let's say you see the confidence interval, but you want to work backwards. Okay, so you're asking yourself, well, what margin of error did they use? So pretend this was not given to us. Okay, we don't know. They didn't give it to us. But we do know this. If we want to work backwards and go, well, what margin of error was used? We would take the upper limit minus the lower limit. After that subtraction takes place, divide by 2. And there is the margin of error. Okay, so we just worked with best guesses and confidence intervals using formulas. I'm going to show you how to use StatCrunch for the next one. All right, looking at this before we actually try to apply it, we're going to be opening StatCrunch, open the Stat drop-down menu. This particular question is about proportions. So we're going to work with the menu Proportion Stats. We're going to open the menu One Sample. That's because at this point in our learning of this science of statistics, we're only working with one population. In Chapter 9, we'll start to compare multiple populations. So we would choose something other than one sample. But for now, we're working with one sample. And we're going to run the program using a summary of stats. We're going to be asked on the input screen what the number of successes is. We're going to be asked on the input screen what the number of observations is. Remember, the number of successes is X. The number of observations is lowercase n. And then we're going to ask that program to run a confidence interval for the true population proportion. Program needs to know what's the confidence level. Default is 95. Other common used ones are 90 and 99. So you'll need to tell the program as a decimal, whatever confidence level we're using. We hit compute, and the output screen will appear like this. The best point estimate, p hat that we've been talking about, the sample proportion, will be in this cell right here. Column total, or column title, sample proportion. This is p hat. Careful with this one. This is the standard error. This is not the margin of error. This cell right here. Don't accidentally use that one when asked the margin of error. L limit and U limit represent the lower and upper limits. If you have this output screen and you're asked what is the margin of error, you can work backwards. You can take the upper limit less the lower and divide by 2. Similarly, if you're not given X or N, but you have the interval, you can work backwards and find p hat using the upper limit plus the lower limit and dividing by 2. Okay, so let's try to use StatCrunch for this next example. They didn't really tell us what it's about. They just tell us that the sample size was 171 and X, or the number of successes, is 124. Okay, construct a 95% confidence interval for a population proportion P, round to 3 decimals. All right, going to have to minimize that for a second and look at StatCrunch. Okay, we were told on the last slide to open the stat menu. This particular question is about proportions, percentages, X over N. So we go to proportion stats, one sample, and we were not given the data. If you're given the data, you'll see it. You would see 100 and, what was it? I can't remember now. It was 171 was our sample size. If you were given that data, you would see 171 cells with data. Oops. We were, on the other hand, given just a summary, the number of successes out of the sample size. Okay, so our number of successes was, I believe, is 124. Oh, goodness. And I closed the window so I can't see it. Out of 171. 124 out of 171. Okay, next thing we're told to do is, or we're telling the program to do, is what it's going to perform. Not a hypothesis test, that's chapter 8. We are in chapter 7, which is on right here, confidence intervals. The confidence level, notice that it has the default there for us, 0.95, so we only need to change it if we were told that a different confidence level is to be used. And then you hit compute. Output screen shows us sample proportion, lower limit, and upper limit. Shrink this. Well, here we go. We have our lower limit to 3 decimals as 0.658 and our upper limit to 3 decimals as 0.792. Part B wants to know the best point estimate p hat, and that is right here for us, 0.725. And then part C wants to know the margin of error. The margin of error can be found by, pick your calculators up, margin of error, you're going to type in the upper limit less the lower limit after you make sure that that subtraction occurs. You can do that by hitting enter, or you can put this in parentheses. Regardless, you have to make sure the subtraction goes first, then divide it by 2. And if you're using your technology correctly for calculating, you should get 0.067. If you're not getting 0.067, it may just be an error with the order of operations on your calculating technology. So pause the video and take your time, work with your technology, make sure you're doing upper limit less the lower limit. After the subtraction occurs, you're dividing by 2. All right, here we have another one about college students and if they own their car. When 334 college students are randomly surveyed, it is found that 103 own a car. We're asked to construct a 99, okay, note that, 99% confidence interval for the true proportion of all college students who own a car. So own a car was just set as our success. Sorry, X, not N. So this is X. And N is the number that we surveyed or sampled, sample size. So we have X, we have N, and we have our confidence interval. You can do this by hand if you want, that we did like we did 2 examples back, or you can practice more with StatCrunch. Okay, I'm going to use StatCrunch. Gotta remember these numbers: 103, 334, and 99%. All right, when you guys have your StatCrunch window back up, you can reopen it so you get the input screen again, but you could also just go to Options, Edit. It brings you back to your input screen, and you could change it that way if you want. Let's see if I remember them. 103, 334. I can see it populated there. Confidence interval, 99, and compute. And what we're going to need is lower limit, 0.25885498, upper limit, 0.357911. So we're going to, oh my goodness, I made a mistake. I'm glad I did this so you could see this. If I entered these in the program right now, it would tell me that I was wrong. You know what actually raised the red flag for me? This will tell you right here on the output screen which confidence level you used. And that just reminded me like, whoa, I was supposed to use 99%. Got to go back. Options, edit. Change that confidence level to 0.99. Now compute, and our limits changed. We're now at 0.24329208 and 0.37347439. Okay, we can see here that 0.243 is our lower limit and 0.373 is our upper. Part B wants us to interpret that interval. Now remember, as statisticians, we have to make sure not to speak as the content experts. So when we speak, it's pretty scripted. It's important to do that to make sure we're not appearing to be the content experts, but rather we're the statisticians. So we talk like this for confidence intervals. Ready? We are, and then we state our confidence level. We are 99% confident that the true proportion of college students who own a car is between 24 and 37%. That's how we put our confidence interval into words. All right, let's go to slide 18. Example, a Gallup poll of 1,487 adults showed that 43% of the respondents have Facebook profiles. Part A, find the 95% confidence interval estimate of the population proportion. Okay, so we've seen in these last couple examples that we're going to need X, N, and the CL. Here's our CL, confidence level, it's the default. Here's our lowercase n, got that. And then we need our lowercase x. Well, they didn't tell us exactly what x was equal to. They just said that 43% was the outcome. So please note this, okay? 43% of that sample size, 1487, is, if you type that in your calculator, you're going to get 639.41. But when you type that into MyLab and Mastering, when you type that into StatCrunch, it's going to want the nearest whole number. So instead of typing in the 639.41, type in 639. So we'll use 639 for the number of successes in StatCrunch. That'll be our X. Just heads up for that. Okay, we have X, we have N, and we have CL. Let's go to StatCrunch and type them in. Just gonna edit this. X was, oh my goodness, 639, I think. And then it was out of 14. I should really be jotting these down or working with something with more screens. 1787. $14.87, sorry. Okay, got to put our confidence level back to the default and compute. Okay, hopefully I remembered those correctly. And let's see if we get our limits accurate to 3 decimals, 0.405 and 0.455. Nice. The best point estimate is right here. It's listed as the sample proportion, 0.430, rounding to 3 decimals. And to get the margin of error, we'll have to pick up a calculator, type in the upper limit, minus sign, lower limit, hit enter, then divide it by 2. After that, we can interpret that confidence interval like this. Oh, it actually, I'm sorry, part D didn't just say interpret it. Part D is asking us, can we conclude that fewer than 50% of adults have Facebook profiles? Write a brief statement that accurately describes the results. Okay, so 50%. Well, we're looking at the interval we created. If you want to see it, calculated rather, as a percent, this right here would be about, because it was rounded, remember, so about 40.5, and this right here would be about 45.5. So we are saying, as the statisticians, that we are 95% confident that the true population proportion of people who have Facebook profiles is between 40.5 and 45.5%. So, can we conclude that fewer than 50%? Yeah, our entire confidence interval is below 50%. So we can say with 95% confidence, it does appear that fewer than 50% of adults have a Facebook profile because the interval is completely below 50% or 0.50. If you need more time to write that down, please pause the video and take as much time as you need. When you're ready, play the video again, and we're going to talk about slide 19. Suppose we want to collect sample data to estimate some population proportion. A minimum sample size based on the confidence level must be obtained. Okay, well, if they want us to be 95% confident or 99% confident or 90% confident, we have to sample a minimum number of people or measurements or data values. How do we figure out what that minimum sample size needs to be? If we have anyone else's studies, if we can find any other study on whatever it is that we're trying to study, and they state their p-hat, then we're going to have to sample less people because we get to use their work to help our confidence interval. Another way to say that, you guys, what I just said is right here. If p-hat is known, okay? If p-hat from a different study is given to us, then this is the formula we're going to use. Minimum sample size is going to be this critical value right here, which I'll show you how to calculate. You'll square that. You'll type in multiplied by the p-hat from the other study. Multiply that by q-hat. You guys know p-hat and q-hat are complements. And we'll divide that by the margin of error squared. Now, if you're studying something and you cannot find anyone else's study, or maybe you can find their study on the same thing, but it's from a biased source, or you don't want to use it for whatever your reason is. Another way to say that is if p-hat is not known, okay? If p-hat is not known, then the best thing we can do for p-hat would be, and q-hat would be 50-50. If p-hat's not known, it's like flipping a coin. 50-50, p-hat, and then making q-hat, it's complement, so it has to be the other 50. Well, it turns out that if you guys pick up your calculators, or if you do this in your head, 0.5 times 0.5 is equal to 0.25. So our formula, it's technically the same formula, but here you see the 0.25. Just want you to know where that came from. It came from this first formula and using 50-50 for p-hat and q-hat. All right, I said I would talk to you about this z sub alpha over 2. Okay, so it's written like this, Z with the subscript, alpha over 2. That's the lowercase Greek letter alpha. We read it Z sub alpha over 2. What this value is, it's the value that separates the likely from the unlikely values. We've talked about that before. Before we used z-scores, same z right here. For standard normal distribution, z-scores of positive 2 and negative 2 were the separators. They separated the ordinary from the unordinary, the usual from the unusual, the likely from the unlikely. Okay, so to find z sub alpha over 2, we can use the normal calculator in StatCrunch like we did before, or just for the 3 most common ones, just to avoid a step in StatCrunch, if you're told to be 90% confident, then your critical value, z sub alpha over 2, is 1.645. If you're told to be 95% confident, 1.96 is that separator. And with 99% confident, we would need that separator to be at 2.576. Alpha is the complement of the confidence level. So alpha right here came from 1 minus the confidence level, but remember it's the confidence level as a decimal. So 1 minus 0.9 gets us 0.1. 1 minus 0.95, that's where this alpha came from. 1 minus 0.99 gets us 0.01. All these right here, you guys, that's Greek letter alpha. It's called the significance level. Let's see it on a graph here. Using the default as our example, visual, confidence level of 95%. That means the likely values, or those having the probability of 0.9, probability being selected of 0.95. That's all on the inside here. And the z sub alpha over 2, well, we've got half of alpha in this tail, half of it, see? Half of alpha in this tail, half of alpha in this tail. And that leads us to the z-scores, if you will, the critical values that separate that 95% from the significance level alpha, which would here, it would be 0.05. Half of it's here, half of it's here, 1.96. So that's just a visual on where these came from. You can obtain these by referring to this table. You can obtain these by opening your StatCrunch normal calculator. You could also refer to the z-score tables that we used to use those a lot, but StatCrunch is a more accurate tool than the z-score tables, which is why we're going to use StatCrunch. Okay, let's try one. Companies are interested in the percentage of adults who buy clothing online. How many adults must be surveyed to have a 99% confidence level that the sample percentage is in error by no more than 3 percentage points? A lot of info there, okay? Ultimately, what you want to gather from that is, well, what are we being hired to do? It's right here. How many? Lowercase n equals question mark. We need to know how many adults need to be surveyed, and we're told we want to be 99% confident, and our margin of error, so it says it in this type of wording, percentage is in error by no more than 3 percentage points. So the margin of error is told to us 3%, but we know we don't put percentages into our formulas. We put their corresponding decimals. Okay, part A says use a recent result from the Census Bureau. 66% of adults buy clothing online. Hey, they just gave us someone else's p hat. It's 0.66. So for part A, we're going to use the formula lowercase n equals z sub alpha over 2 squared times that 66% multiplied by its complement, which is 34%, all over 0.3 squared, 0.03 squared. It'll look like this. I want you to pause the video and type that into your calculator. Go ahead. Welcome back. Let's see how you did. If you got 1654.520129, then you typed into your technology correctly. If you didn't, maybe you just forgot one of the squares or forgot to hit the division bar. So try again. And our final answer, however, will be to the next whole integer, so 1655. Okay, so we would have to find or sample 1,655 adults to be 99% confident on the percentage of adults who buy clothing online. Okay, part B, assume that we have no prior information. So we don't know p hat. That's gone. We don't know this. We're pretending we don't know this anymore. So we're going to use the second formula. Plugging those values in, z sub alpha over 2 is our 2.576 again. P hat times Q hat, well, we don't know anything about them, so we got to go 50-50. 0.25 divided by our margin of error squared. Go ahead and pause the video and type that in your calculating technology. Welcome back. If you got 1,843.27111, nice job. If not, maybe you just forgot a squared, so just try that again. And remember, for our sample size, this is the minimum that needs to be sampled. So if we followed the regular rounding rules, this would be closer to 1,843. But for sample size, since that's the minimum, the 0.27 is included, we would have to sample one more adult to get to our 99% confidence. So without the Census Bureau's previous study, we have to survey an additional almost 200 people from here to here. Well, that makes sense because we're not using any past statistics. Okay. How many adults need to be surveyed in parts A and B if we are to be 90% confident? All right, so what we're going to do now is just redo part A, but with 90% confident, we want to see what changes. What changes from here to here? Well, we know that 99% was the confidence level up here, and down here it's 90%, but what does that affect? And what it affects is the z sub alpha over 2. It goes from the 2.576 for 99% confidence level to the 1.645. Pause the video, type it in your calculator. And if you did that correctly, rounding up, it would be 675. That is significantly less. That's almost 1,000 less people that have to be surveyed when our confidence level changes from 99 to 90. Interesting. All right, we're redoing part B, but with 90% confidence. So our 2.576 z sub alpha over 2 changes to 1.645. Pause the video and type that in. And hopefully you got 752. That is how many adults need to be surveyed, not using any other past data, to be 90% confident in our confidence interval. All right, you guys, that concludes our discussion for section 7.1. My name is Jami Emigh. Thank you for joining me, and I will see you next class.